Good morning and welcome back to Manitoba Agriculture Crop Talk webinar series. Again, if you have any questions during the presentations today, please type them into the Q&A icon on your Zoom toolbar and we'll get to them at the end of the presentation. This webinar will be recorded and you will receive a link to the recording. Thank you.
Thanks, Lori, and I'd like to welcome everybody to a few of our winter crop talk sessions. We're talking and had a few things we maybe wanted to discuss, so we figured we'd do a few here before we got right into our spring crop talk sessions. And today we have Marla Rickman coming on, and she's going to be talking about managing our soil pH. I guess it's a it's something that doesn't get a lot of attention, but when people start talking about it, it's always good to get a lot of the information out as to how to manage soil pH, what is soil pH, what we should be thinking about when we start looking at trying to change or develop our soils and changing our pH levels. So I thought it'd be a great opportunity for Marla to come on and talk about that. And we'll go from there. So right now I'll let Marla grab the screen and we will start with managing our soil pH.
Okay, can you see everything there? Well, Lionel? Lori?
You bet, everything looks good.
Excellent. Okay, so we are going to talk a bit about soil pH today. I know there's often a lot of questions, and like Lionel said, it's not like a hot topic in all areas to be able to discuss, but I think it is good to be able to have these discussions around issues, whether it is having high pH, low pH. And there's often questions that come up around how to manage it, how do we deal with it, that sort of thing. So I want to start off just as a reminder again about what soil pH is. So what pH is a measure of hydrogen ion activity in the soil. So essentially how much hydrogen you have, that is going to be kind of related then to that pH number, that pH scale. So we talk about things being neutral, being of course 7, and then if you're above a pH of 7, that means you have less hydrogen ion activity. This is a negative logarithmic scale, so it means that the number change between, say, a pH of 5 to 6 is a decrease of 10 times the hydrogen ion activity. And then from 6 to 7 is another 10 times. So because it's negative logarithmic, it means that the change from 5 to 7 is actually 10 times 10, so 100 times of a decrease of hydrogen ion activity. And then, of course, the negative kind of logarithmic scale here, that's what's actually associated with the pH number on that scale. So when we talk about productive soils, we're often talking about soils that will be somewhere within the realm of a pH of 5.5 to 8. There's a wide range, and soils, of course, at neutral are never considered right at 7. We kind of consider a neutral soil to be anywhere between 6.5 to 7.5. There's a lot of variability in there, but just wanted to kind of give that reminder that what we're talking about is how the presence of hydrogen or the activity of hydrogen that is available in those soils. So again, as you get into soils that are above 7, a soil pH with kind of essentially less hydrogen ion activity, they become basic. And as you get into soils that are below 7, then those ones are considered to be acidic. Now, when we look at soils kind of across North America, and especially in Manitoba, we often talk about soils having a high pH. And generally speaking, we do see soils that are at a high pH. The number of soils, this is some older data, obviously from 2001. The number of soils in Manitoba that were listed at this time was showing that like less than 10% was actually showing soils that had a pH of 6 or lower. So soils that we would consider to be more acidic in nature. Alberta has a much higher percentage of low testing soils or more acidic soils. And then we see in different areas like along the eastern seaboard, kind of into that area of the central kind of the US, there is a range then of soils that tend to be a bit more acidic. And if you look down kind of again, anywhere where you consider soils to be either sandier or more weathered. So soils that have higher precipitation and have more leaching over time and weathering as they've developed, you tend to have a lower pH. And that's because over many, many years, you've got hydrogen or the more basic cations, things like calcium and magnesium, leaching slowly through those soil profiles, and it leaves that hydrogen behind. And so those soils tend to have a higher pH. Again, in Manitoba, we don't have a whole lot of low pH soils. They are definitely in pockets, and we see those in areas where we have lighter soils. So sandier soils here in that Assiniboine Delta, those wet sands in the southeastern portion of the province. Those are areas where we tend to see a higher area than of having more acidic soils. Again, soils that have leached, that have a higher percent of sand, and therefore have more water movement and leaching of those basic cations down deeper into the profile, leaving more of those, the more acidic ions like aluminum and hydrogen behind. So given that, then soil pH is affected by a number of different things. As organic matter decomposes, acids are released, and so that can show a decrease in pH over time. The parent material will be a part of that, again, depending on the components of the parent material. So our parent material tends to have more of a basic nature to it because it's limestone based. A lot of that calcium, magnesium, those more basic ions exist in that soil. And so as a result, our soils are naturally higher in pH to start. Precipitation, as you have higher rates of precipitation, you start to see the potential for acidity to build up because, again, you have some of that leaching. The native vegetation, the types of crops that are grown, that is often related to the fertilization and how much nitrogen fertilizer is applied. So nitrogen fertilization, especially with, ammoniacal nitrogens, things like that, that can end up seeing more acidity build up because as that NH4 is transitioned or changed over into nitrate in the soil, then that hydrogen is released, and that hydrogen is what helps to build up that acidity. Flooding can also shift pH. After soils have been flooded or they're fully saturated and waterlogged for a period of about a week, the pH kind of comes towards neutral. Whether that was an acidic soil or a high pH soil, they can kind of come towards neutral. And as a result, that can then shift that in a short term. As soon as those soils are no longer flooded, that pH will shift back to what its kind of natural unflooded state would end up being. So one of the things that kind of we recall, especially as we go through this presentation, talking about changes in pH over time, is that, again, particularly nitrogen fertilization can speed that rate that acidity develops. Acidity will develop very slowly, again, as soil weathers, as precipitation falls. This is a natural occurrence, but it's a very slow occurrence. But we can speed that up, especially if we're dealing with, ammonia-based fertilizers. And we do see that, generally speaking, the soil and soil pH in Manitoba is declining over time. So this data is looking at the change from 2001 to 2015. This is data shown by the International Plant Nutrition Institute. And what they're showing here is that the pHs that have been primarily in that 8.1 to 8.5 range, the number of soils that we're testing in that range over that 15-year period has decreased by about 6%. And so again, it just means that there's been a slight shift and we're seeing this increase in soils that are starting to fall then within that more neutral range, and an increase slightly in soils that are in that more acidic range. So the soil pH is shifting. And again, that will happen naturally over time, but it is being sped up in some cases by different occurrences, whether it's, more decomposition of organic matter, but nitrogen fertilization being one of the key factors. So we want to know our soil pH. It is important to understand this, and it's a simple part of that soil test that we look at. And it's actually one of the things that we'll look at from a soil health perspective to understand where our soil pH is sitting. And the reason why we want to see that is that we want to watch for any more like rapid changes that are happening. There's a few key things that we look at then or think about when it comes to that soil pH. Some plant species have very specific pH requirements. Some plants will be more tolerant of acidic conditions or more tolerant of alkaline conditions, and that can help us to target certain plant species based on that. Now, that being said, if you go down into the States where some people see some of our high pH soils because they don't have as many high pH soils, and they're completely shocked that we can grow, wheat crops and things on soils that are around that high pH, in that high 7s to 8s, low 8s. It's completely shocking because theoretically it shouldn't happen that you can get really big wheat crops on those high pH soils. But the reality is that we can grow crops on this range of pH soils. So, take that with a grain of salt. Legume crops tend to like being in the neutral to alkaline soils, however, and that is because the bacteria that infect those for finding nitrogen and such, they tend to survive better in those alkaline soils or higher pH soils. Cereal crops, again, like wheat and oats, tend to like more acidic to neutral conditions in that 6 to 7.5 range. But again, we grow excellent wheat crops and higher pH. It doesn't mean that you can't grow something outside of that range. Potatoes tend to like more acidic to neutral conditions at lower pH. And that's because things like fungi and scab and some of those diseases tend to be worse in higher pH soils. So that's one of the reasons why that acidity can be very helpful with potatoes. Also, of course, potatoes with more of an acidic soil tends to be a sandier soil. So there's that other side of things that the potatoes like to be in those lighter soils to begin with. Things like cranberries and blueberries, we find these naturally growing in lower pH soils. They like that more acidic to medium acidic range. And so that tends to be one of the questions that people will get is, well, how do I shift my pH down if I'm trying to grow something, say, like cranberries or blueberries? Again, when we talk about certain crops liking different soil types, quite often it is because of the whether it's the nitrogen fixers, the bacteria that prefers to be in a neutral, even up to a higher pH soil, like things like alfalfa, that can be very helpful. If you think about alfalfa seed production, we do a lot of that up in the Interlake, and that's when we're dealing with a lot of those higher pH soils, because again, we end up with higher pH as a result of having that high limestone base to those soils, whereas potatoes, again, and the fungi not really loving that lower pH soil, so actually can decrease some of those issues with potatoes. So again, another reason why we want to know what our soil pH is because it links to productivity and it has a very big influence on the nutrient availability of plants. Now, in general, when we look at the range of kind of availability of different nutrients, we find that in that neutral range, that 6.5 to 7.5 range, that tends to be where most of our nutrients are at their most available. If you think about something like phosphorus, we know that as soil pH increases into those more alkaline levels, this is where phosphorus availability starts to decrease. Potassium availability can decrease. On the other side, you also have a decrease on the more acidic side because phosphorus now is going to be tying up with, say, aluminum in the soil rather than tying up with that more basic cation of calcium on the alkaline side. So it gets tied up either way. It's just a matter of how tied up it ends up being, whether the soil is more acidic or more alkaline. But generally speaking, again, neutral soils tend to have a higher amount of available nutrients. And that's why we want to think about that as being, the better, air quotes, soil range for pH, just because of nutrient availability for crop growth. So if we're talking about the acidic side, I want to focus on that first, and then we're going to talk more about the alkaline side. And again, the acidic side, we have less soils that are in that area, but we do need to think about this because acidity, as soils that are in that neutral range might be slowly marching down a little bit. We need to think a little bit more about lower pH soils and how that can affect plant growth when we do deal with them. So again, availability of nutrients like phosphorus, potassium, molybdenum, these things can be reduced. The symbiotic nitrogen fixing bacteria, their activity is reduced because they don't like to kind of function in those more acidic soils. We also know that soil applied herbicides, and if Kim is on later, she can answer more of this. But when we're talking about things like soil applied herbicides, their performance can be decreased when you have more acidic soils. And so that's something to think about if you have anything that needs to have any carryover, or we want to decrease, let's say, some carryover as well. Soil pH can can play into that. And then clay soils that have high acidity are actually less highly aggregated. And that's because high acidity means less of the basic cations. And those basic cations are things like calcium and magnesium. And they are actually helpful in building soil structure because they aggregate or flocculate or draw clay sheets and clay particles together in that soil. But when you have less of them available, it means that you'll have less of that aggregation. So clay soils that have a lower pH, when that does happen, and it can happen in some cases, some pockets in Manitoba, where you have that, you can have a decrease in soil structure, let's say because of less of that aggregation showing up. We can also see maybe a reduction in the breakdown of organic matter, just because, again, those organisms, the bacteria, things that are a part of that, don't like to function in that soil acidity. And so we may have a lower rate or less mineralization of nitrogen during that breakdown of organic matter. We could potentially have calcium deficiencies. More likely, we'd see a magnesium deficiency. But again, in those extreme situations, calcium and magnesium can be missing or lacking in those soils because, again, they are the basic cations that are in more alkaline soils. In an acidic soil, they're not present or they have leached out of that surface. And so you may have less of them available for as plant nutrients. And then the other thing that we can see is potential toxic levels of things like aluminum, iron, and manganese. And that's because in an acidic soil, especially a wet acidic soil, you can have an increase in solubility. And if you think back to the slide where we showed where the nutrient availabilities are and how they're restricted at different pHs, things like aluminum, iron, and manganese are actually at their highest availability in more acidic soils. And that can be good because, of course, things like iron and manganese are nutrients, but they actually are available at such a high amount in those wet acidic soils that they could actually cause toxicity. So these are photos that Lyle Powell now of Nutrien has taken and shows some situations where manganese toxicity was showing up in canola. It's got this very weird look of it where you kind of get this almost bubbling of that canola leaf. And again, high acidity, so low pH, and wet soils. So wet, sandy, acidic soils in this area of northeastern Saskatchewan showing this issue of manganese toxicity starting to show up. And this is something we actually have seen in Manitoba as well. So this is some photos that John Hurd had taken a few years back where he had been called by an agronomist to come and take a look at a field which was having very patchy, odd growth or lack of growth, as you can see in the forefront of these photos, of canola on sandier soils near McGregor. And when they looked at the pH of the soil and looked at the composite sample, the pH was around 6.1. So not that far out of that 6.5 to 7.5 neutral range. Doesn't look like it should be an issue, but you can see that the canola off in the distance is growing a lot better, even though not great, but better than this kind of large patch here in the forefront of the photo. So what they did was they took a composite soil test. They actually compared the composite soil test, I should say, to where they actually took soil tests in the poor growing area versus the good growing area. And what they found was when they looked in that poor area at the front, where again, there's very patchy growth of this canola, the pH was actually in the top surface around 4.6, 4.7. So far off from that 6.1 that the composite soil test was showing. And I think it's really important to note here too, when we look back at this picture, there's definitely a wide range of things that we end up seeing here where you can see if you think about the patchiness, there's a high amount of variability in the soil. You can see that because the crop is growing quite variably. pH is one of those things that, again, it's very tied to how water flows through the soil, what the soil texture is like, and these things can be highly variable across a field. So as a result, again, it's important to think about the fact that pH can vary widely across the soil, and that's what this test is showing. The composite test, when we averaged it all together, was around 6.1, but when we actually look at the poor growing area, it's so far below that it's important to recognize that we need to understand better what's happening in those areas and maybe think about that high variability. Again, sandy soil, this is that soil profile you can kind of see in the small probe here. And over a period of time, lots of soil has or water has leached through that, causing some issues, low pH showing up. The soil test down below, 6 to 24-inch depth, ranged from 5.7 to 6.7, so still quite low. And comparing that to the composite that showed that it was 7.3. Again, the range in this area or this patch of the field is much, much lower than what the rest of the field was showing. So when they did soil tests to take a look at this, what shows up here is the manganese. Now, manganese, if you're looking at your soil test, is obviously, generally speaking, going to be a lot less than this. This is a very, very high number. So is that 133.3 that's for the iron above it. Both of these are considered to be very, very high. And when they're very, very high like this actually can be a risk, especially if you're looking at soil pHs that are down in that below 5 range. The other thing on this is that the soil test aluminum was 32.8 parts per million, which is also considered to be a very high number. Now, soil test aluminum is not on your typical soil test. That becomes an add-on. We don't normally look at aluminum in a soil test because it's not a necessary nutrient to take a look at. But again, in this particular case, they asked for that additional test because of the fact that we wanted to know whether or not aluminum was actually at toxic levels causing problem in the plant. And of course, when you're looking at patchy growth, you want to look at tissue testing as well to know what is going on. So here, John was comparing the worst canola in the patch where it's very not much growing compared to the poor canola. There is no good canola in this field. It wasn't great across the entire field. And when you look at that here, this manganese is very high. The nutrient sufficiency range for manganese is up to 100, and this was 1,572. So well above that number, which is showing that we're probably showing some issues. Aluminum here, 129 is the number for parts per million coming up for aluminum. There is no kind of note of whether this is very high. It's not something we're looking at as a sufficiency issue with crops, but that number is very high. And in the better but not great growing crop, we still see this issue here where we've got, 162 for that manganese. It's still outside of the sufficiency range, but problematic. And same with the aluminum. Now, one of the things we really need to point out on the aluminum is that tissue aluminum tests, if you're ever looking or worried you have this kind of problem, tissue aluminum tests are not reliable. And the reason for that is that aluminum toxicity tends to damage the tip of the root, and it will restrict how much aluminum is translocated to the upper part of the plant. So this number would have been higher if the plant could potentially take up more aluminum, essentially, is what could have happened there. So if you have an acidic soil, if you're dealing with soils that are in these ranges where everything is very low like that, we may want to look at increasing that pH and with using lime or any other kind of basic product. So if you have, again, a soil test, I'm just going to click back here to show this. Sorry about the jumps. If you have a soil that is testing down below 6, it will then give you, if you send to a test like AgVise, they automatically will give you a buffer pH. And we need to know what that is because that is what helps you to calculate then how much lime needs to be added. So understanding your buffer pH is going to be important. And then when we make a determination then on how much lime to add, the reason we want to do that is because it's going to decrease those potential metal toxicities or aluminum toxicity. It can improve the physical condition of the soil, again, because soils that have low clay content, low calcium content will tend to have less structure to it. And so adding that calcium in the lime can help to build some of that structure again. It's good for stimulating microbial activity. Again, those microbes tend to like neutral to higher pH soils. So as a result, lime can help to improve that stability or that activity of microbes in the soil. It can increase that CEC if you've got variably charged soils, and that's just because we have more charges essentially that's added. It can help to increase the availability of nutrients. Obviously, again, things like phosphorus can be impacted negatively when we have low pH soils, and so that can bring that back up again. The calcium and magnesium that are in that lime product they're also considered nutrients, and so they can help supply some of that nutrient to the plant. We end up again, not just with higher microbial activity, but more of that potential for nitrogen fixation in legumes because those microbes prefer the higher pH. And generally speaking, this can improve crop yields. So liming is not something that we would do just once. It is something we may have to do more than once because the soil may buffer some of that change. So the total amount of lime that we have to apply to the soil is going to depend on the soil pH, going to depend on that buffer pH, and the CEC essentially of that soil. So the higher the clay content, the higher the organic matter, therefore the higher the cation exchange capacity of the soil, the more the soil can buffer any change that we're trying to make to that pH. And therefore we need to add more lime in order to make that change. So we look at those when those calculations are being done. So if you're talking to an agronomist or trying to figure that out, looking at those ag lime calculations, we have to look at the quality of the lime, how kind of essentially what the pH, like the liming activity of those different lime products are. And then you're going to look at the soil pH and the CEC, and we're going to make those calculations then based on those pieces of information. Now, again, soil samples with low pH, there's pockets of areas in Manitoba where we would be looking at having to lime or looking at having those low pHs. But generally speaking, our soils are in the neutral to alkaline range when we're talking about soils in Manitoba. So this is the most recent data coming from AgBias from last year's soil tests and looking at the percent of soil samples that come in with a soil pH above 7.3, so above that kind of in that neutral range. And obviously a lot of them, because that is what our issue typically ends up being. So wanted to focus instead on the idea now of high pH soils and what we need to think about. Sometimes people talk about acidifying or lowering the pH on high pH soils. I think it's important to note that it is potentially possible, but there are some restrictions in terms of what that possibility is, and I'm going to walk through them and what we need to watch for if we were ever thinking about trying to lower soil pH. The reason why people are focusing on acidifying high pH soils, again, is to increase the phosphorus and micronutrient availability. Those high pH soils tend to have lesser phosphorus availability, lesser micronutrients. So the idea is to bring that soil from the high pH down to a more neutral pH to try to hit that sweet spot where everything is the most available. And then the other reason is that people might be wanting to grow crops like blueberries as a specialty crop, things that like more acidic pH. So then you're trying to take a soil from a more neutral level right down to a more acidic range because of a specialty crop. So this may show up, these questions will sometimes come up in the market garden and kind of smaller producers that are looking at berry production and trying to figure out whether or not they could get into cranberries and blueberries as a specialty crop. And of course, the other reason is to modify microbial activity because bacteria tend to like high pH soils. So if you're trying to grow something like potatoes, you want to have that lower pH because that low pH can reduce things like scab. So the way that you could potentially acidify a high pH soil is by using elemental sulfur. And the reason for this is because the process of oxidizing elemental sulfur into sulfate, which is a microbial activity, will actually release hydrogen. And more hydrogen means more acid essentially in your soil. So in order to look at lowering high pH soils, you would add elemental sulfur. And if we look at some of the recommendations out there, so OMAFA, um, they have a recommendation on loam soils at a pH of 6.5, you would add 2,400 pounds of elemental sulfur per acre for 2 successive years to lower the pH to 5. And that's for people who are looking to grow blueberries. So again, you're starting with a soil that's already on the low end of neutral and taking it down into acidic soil. But their recommendation is that as soon as you have a pH that's greater than 7, it's not advisable and quite impractical to lower the pH because of how much sulfur would be required. Because again, as you get a higher pH, you have to add so much more sulfur in order to bring that down. And so that brings us to some studies that have been done looking at trying to decrease soil pH. Now, this is a study from South Dakota. And when they looked at this pH starting at 7.8, they were able to, with up to 8,000 pounds of sulfur per acre, lower that pH to 5.7. So the OMAFA recommendation is saying, it's a lot of sulfur that has to be applied in order to get it down to a low number. And this is showing exactly how much sulfur we're talking about. So then is it really feasible to bring that down? What's interesting to note here, though, is as we would expect, the availability of phosphorus and micronutrients is increasing. As you look down these columns, you can see that the numbers are going up. And that's because as the pH is lowering, the availability of these nutrients is increasing. And that's what we're looking for. This is why people might want to be lowering pH to increase the availability of these nutrients. But a very important point that I want to make here is at the end, the electrical conductivity or the salt content of these soils, which started as a non-saline soil around 0.4 electrical conductivity, 0.4 millimoles per centimeter, is going up to 2. And that's because sulfate is a salt. And when we add excessive amounts like here, so that every one of those elements of sulfur, that S alone is going to change into sulfate, SO4 2 minus, right? So we're going to add oxygen to it, but each one of those elements of sulfur ions is going to become a sulfate ion. And as a result, we increase the salt content. So this is a soil, again, the pH was lowered, and the nutrients were more available, but the risk that came along with this was an addition of salt. And is that something that you actually want to do if you were trying to lower your pH? Now, AgVise has talked about this in the past. Yes, again, this is looking at some of the changes using elemental sulfur. This was a 10,000 pound elemental sulfur for a high pH soil starting at 8, and it dropped that down to 7.5. So again, not super low, again, because it takes a lot when you've got a high pH soil to bring that down. But 10,000 pounds per acre, and over time, it crawled back up again because this is not a permanent change. These soils are naturally wanting to stay in that high pH, kind of buffer it over time. The other thing that we need to note is the soil carbonate level. This is calcium carbonate equivalent. It shows up on your soil test. It's essentially a measure of free lime in your soil. How much limestone is kind of ground up and floating around that can be in soil solution when that soil gets wet. And this is 2.5%. The previous slide was under 2, it was 1.3 or something like that. So take note of that, because another test, all done again by South Dakota State University, looking at a different soil test or a different soil type that had varying amounts of calcium carbonate equivalent, shows that the more of this free lime you have in your soil, the harder it is for your soil to change in its pH. So starting off again with all of these soils in that higher, just above 7 pH range, very little calcium carbonate, very little lime. It's not buffering that pH change. It was very easy for them to drop the pH. You increase here to 1.6. It's dropping, but not as significantly. You move this up to 6.8%, and now this isn't going down. Now, it's really, really important to think about this, because if you are looking at a higher pH soil, as we tend to have in Manitoba, we need to make note of whether or not you would actually have the ability to lower that pH based on the calcium carbonate equivalent. This 6.8% is equivalent of 68 tons per acre of limestone in the top 6 inches. That's kind of what that means. In Manitoba, this is only a moderately calcareous soil. Some soils in the Interlake can exceed 60% CCE, not just 6.8. And this is looking at, again, soils that are based on limestone in our Manitoba kind of parent material that our soils are created on. Extremely calcareous soils exist, especially in this Interlake region where we're above 40%. Lots of areas in kind of around these ranges, even down in this low kind of area around the Red River Valley, very strongly calcareous. So that 26 to 40% strongly throughout most of southwestern and western Manitoba, northwestern Manitoba, in the 16 to 25%. There are very few soils that are going to be in that weakly carbonate soil area of 1 to 5%. And again, they are going to be on those sandier soils, which tend to have a lower pH to begin with. So again, it's really important to take note of that. If we're trying to acidify soil, it is really futile, it's very expensive, and it's likely going to increase your salinity quite a bit. So it's important to think about that because it's just not something that we can do in our soils in Manitoba based on that parent material being so high lime. We do need to think about phosphorus and microavailability because they can be decreased when we're talking about high pH soils, but that's why we banned our phosphorus and micronutrients. The importance of banding to decrease the contact that the soil has with the fertilizer is very helpful. Quite often too, when we think about things like, say, monoammonium phosphate, it has a very low pH to begin with. It's highly acidic. So if we create that band will be more acidic. And so it will make that phosphorus more available in that small area of the band as the root is kind of growing past it or near it. So that becomes really important. Now, of course, we want to make sure we don't put too much fertilizer down really close to the seed. But when we're talking about putting some of these specific fertilizers down that have decreased availability in high pH soils, again, decreasing how much soil it comes in contact with is really important. And this is why banding has always been kind of a number one use of these nutrients, especially in those high pH soils. Works very well. So a couple of quick take-home messages here. Soil pH, again, can be very variable across the field. We want to think about where we're looking, and we want to watch for these patches that can show up over time, especially on sandy soils. If we're growing, high nitrogen-loving crops and using high nitrogen fertilizer, that can decrease that soil pH over time. Given that, though, acidic soils can benefit from liming, we can improve yields, we can increase nutrient uptake and decrease the potential for some of these toxicities of heavy metals in the soil or in the plant over time. And then on the flip side, when we're talking about high pH soils in Manitoba, we just cannot acidify them easily. We need to take note of our soils being very different than what we expect to see in soils that are elsewhere in the world. But the amount of limestone or that high calcium carbonate equivalent that exists in our soil buffers any pH change, and it really isn't possible to decrease the soil pH of our high pH soils. It is much more important to focus on placement of fertilizers, especially ones that can get tied up in those alkaline soils like phosphorus. So make sure that we're banding them, having them close to the seed. And that is what increases the availability of those fertilizers over time when we're dealing with soils that have that high pH. So that's what I have for you today. If there's any questions, I'm happy to take them. Otherwise, I pass it off to you, Lionel, to take over for the panel.
Hi, Marla. There's just a couple questions. One is over the past few years, a lot of producers have been putting a lot of broadcasting a lot of sulfur in the fall. And would that broadcasting have any effect on soil pH?
It can technically lower pH with that oxidation process. Now, if we're not talking about thousands of pounds though. So we do have that slight lowering of pH that can happen, but I would put it in the same range as, you know, the nitrification or the nitrogen fertilizers, that it is a slow process, but it is something to think about as we see that application of an elemental product that can over time slowly start to creep that pH down. But again, if you're going to have a really quick change with something like elemental sulfur, you'd be putting thousands of pounds on to see that.
Okay. What about growing forages or sowing some land down to forage? Would that have a long-term effect on changing pH?
Uh, it would if you with your growing, say, you know, a legume type forage where you're not adding the nitrogen fertilizer. It would the soil would stay a little bit more stabilized for a longer period of time in those cases. So if we're it's I would say less about the type of crop necessarily that we're growing, but more about the way that we're fertilizing them. If we're seeing that creep down, especially again on those sandier or lighter soils that tend to not buffer that pH change as quickly or as easily. So again, that would be soils that, you know, in that sandier range, if they're not getting the same high amount of nitrogen fertilizer, they wouldn't shift lower as quickly as we would see others.
Okay, and you showed on the soil test that was 0 to 6 and 6 to 24 for your pH levels, and they were different. Can you? So is it best to take a 0 to 6 and 6 to 24?
Yeah, so when we're doing 0 to 6, 6 to 24 inch sampling, we're doing that for a number of different reasons as well. Um, Nutrients like phosphorus and potassium that aren't and micros that aren't mobile in the soil tend to be restricted to that top area of the soil. So when we're looking at 0 to 6, we're looking at all of that suite of, you know, phosphorus, potassium, micros, all of that, but we're not looking at those from the 6 to 24 inch depth. That is where we're looking at the mobile nutrients like nitrogen, like nitrate and sulfate that are down below. It is important though to know the range for pH. It's also one of the things we, you know, if soil is being eroded from the top, you know, on high knolls and things and being lost over the surface, we can see some of that kind of creep down because you've got less of that topsoil left in that top 6 inches. So it's important to know if you've got soils, typically speaking, again, our soils in Manitoba, because they have that limestone base, will have a higher pH down in the 6 to 24 inch range. There are a pocket of soils that are acidic in Manitoba, the Kelt soils that are west of Dauphin. In that area, the pH actually increases as you go down. Where there, the pH is like 3.5 in that subsoil. And that's a very different soil. It has a very different, like the parent material of that soil is a little unique. But generally speaking, again, we have a higher pH down below. And when that becomes important for us is when we see some of that erosion of topsoil and more of that high pH soil that's being left at that surface, that can actually impact us a bit more negatively sometimes with fertilizer use or crop growth as well. So it is important to note, it's really important and critical to watch the surface because the surface is where the changes will happen more quickly over time. That's because that's the depth that the nutrients are being applied to. So that's what we're looking at when we're seeing surface versus subsurface.
Okay, thanks, Marla. And I think the next question I see Kim is on, and you kind of referenced this at the earlier on in your presentation regarding herbicide. And I was just wondering if Kim wanted to make a comment on how pH levels in soils may affect some of our herbicide use.
Hi, can you hear me now?
You bet, Kim.
Yeah, sorry about that. I was trying to unmute and it just wasn't working well. Anyways, yeah, you do have to watch for some of our soil applied herbicides, especially you do need to be careful because of there's certain limitations on some of our herbicides. So I'm thinking something like Authority, we have to watch above certain pHs, you shouldn't be using it. And so there are some herbicides that you need to be aware of. And then also there's on the flip side of that, the year after using a herbicide, herbicide pH can affect herbicide carryover for some of our herbicides, like things like our IMI or our group 2 IMIs, like our Pursuit, our Odyssey, our Solo, those type products. They carry over at higher pHs, whereas other products carry over at lower pHs. So there's a couple of things in there. There's like, the pH of the year that you apply will affect certain products. So you do need to watch that, but that is all on the labels, which are in the product pages of our Guide to Crop Protection. So those are there. So those are to be aware of. And then also you do need to know what your pH is when you're talking about carryover for some of these soils. So yeah, pH is pretty important for a few products anyways.
Okay, great. Thanks, Kim. Thanks for coming on and answering that. Now, just a few more slides to finish off for today. Just wanted to mention that back again this year, we will be having our crop scouting panel. So I'm glad that they're going to be available to assist in the crop talks for this coming year. The ones we're having right now, we don't have a lot of in the field type questions. So the questions to the panelists is going to be limited, but once we get into the season, we'll have the full panel on. Just a couple more slides here. If you've got any questions, our crop production extension specialists, some things will be changing throughout the year here, but right now these are the people that are working throughout the province. So if you have any questions, there's our names and contact numbers. Our livestock people, again, the names and contact information are there. If you have any questions, it's been cold. Cattle are going to be suffering a bit from all this cold weather. So if you got any questions regarding feeding and keeping everybody healthy and fed well, it's a good opportunity to take advantage of the knowledge that these people have. Also, Stock Talk,
Oh, we may have lost Lionel. He's having some technical difficulties. So I'll just kind of finish this up a little bit if I can. Stock Talk will be continuing. As you can see, there's a couple dates of March 13th and April 10th coming up. And we may lose Lionel's presentation here briefly. Are you back, Lionel? Nope. Okay. And I'm just going to pull up his presentation here. 1 minute. One second, patience for 1 minute with me. That'd be great. All right, so there's the MASC service centers, phone numbers and locations if you need to give them a call. We have
Lori,
yes.
Not displaying correctly on our end.
No, thanks. How's that better?
No, I'm still just seeing the crop stock talk slide. Oh, there we go. Perfect.
Okay, thanks. So those are our MASC service centers and their phone numbers if you need to give them a call, our agriculture toll-free number at the bottom and MASC toll-free number. If you have any questions regarding anything this week or for next crop talk next week, you can give Lionel or myself an email or give Lionel a call. And I guess with that, we will see you all next week.